Dear students, welcome to our next lecture on the concept of precipitable water, which I think is important to understand before we go into the module of precipitation. And in this video, we will understand the concept of precipitable water with help of an example. And again, we will put all the concepts that we have learned so far to use. So precipitable water tells us that given an air column, let us say we represent it in some nice shape as a cube, and we say that we want to estimate that if entire water that is present in this cube precipitates, how much kilogram or gram of precipitation we are going to receive. Mind it that not all the water vapors that are going present in this cube are going to precipitate. So this is the maximum amount of water that can precipitate and hence called as the precipitable water. And if we know the volume of this cube, if we know the density of water vapors that are present, we can simply say that mass of vapors that are present in this cube should be equal to rho v times volume. However, calculating density of water vapors directly may not be easy. So what we can do, we can use some basic formulae that we have learned, that we know that rho v upon rho a is equal to specific humidity or omega, which implies rho v is equal to omega times rho a, which implies mv can be written as omega times rho a times volume, and this volume would be the cross-sectional area multiplied by the height of this element, which we generally represent by dz. So this is the mass of water vapors that we are going to estimate. And we also know that this specific humidity can be estimated as 0.622 vapor pressure divided by the atmospheric pressure or air pressure existing at particular altitude. So once we determine E, once we determine P, we should be able to calculate the mass of vapors present. And to calculate E, we either need to know the relative humidity or we need to know whether air is at saturation or not, so that we can estimate this E as ES, which is given as 0.611 17.27 times temperature divided by 237.3 plus temperature in degrees Celsius. So putting all these ingredients together, we should be able to estimate the volume or the mass of water that is present in a given atmospheric column. However, we learned last time that as the properties of air changes, all these temperature, all the measures of pressure also change. For example, as we go up, temperature decreases. As we go up, pressure also decreases. So we have to understand how we can measure these values of E and P at different heights, which would influence the values of omega, and calculate the total volume of water that is present in 10 kilometers of height. So how we proceed? What we will do? We will divide this atmospheric column, which is extending up to a height of 10 kilometer, into smaller units. Let us say that we go by a height of 2000 meter and so on. So we will divide this entire atmosphere into 5 chunks, each chunk of 2000 meter. We will call this level as Z1. We will call this level as Z2, and we will measure all the properties, that is pressure, temperature. So I should write P1, temperature, and hence the E1 at these levels. So Z2, P2, T2, and E2, all these things would be measured at these levels, which can give us the magnitude of specific humidity, which we can plug in the formula and get our answer as an average for these columns and add up all the values to get the total precipitable volume of water that is present in the atmosphere. But here we have to use some basic relationships, that how this temperature is varying, how this pressure is varying. So we will use three fundamental equations. First one is that dP upon dz estimated minus rho g. Pressure of air can be estimated as rho a RAT. and rate of temperature with height is given by this lapse rate, which is dt by dz equal to minus alpha. And we have already touched upon all these equations into our previous lectures, where this is hydrostatic law, this is our ideal gas equation, and this is the lapse rate equation for temperature. And now if we can substitute some values, we can always write dp by dz as minus pg upon RAT by substituting the values from 2 into 1. So I've substituted the value of rho A, which is estimated for the air column, which has the composition of vapors plus dry air. And I can simplify this as dP upon P equal to minus G RAT upon into dz. And I know that this dz can be written as minus dt upon alpha from the lapse rate equation. And when I integrate it between P1 and P2, between T1 and T2, I get an expression that log of P2 upon P1 is equal to GRA alpha ln T2 upon T1, which implies pressure at level 2 can be written as P1 T2 upon T1 G alpha RA. Now we have learned that the variation in RA with specific humidity is less, so we can assume RA to be constant throughout the atmospheric column. But you can also do an iterative calculation, but it is not going to add much value, and you can try it yourself. So we will assume this RA is constant as 287 joules per kg Kelvin. And again, G is fairly constant for the atmospheric column, which will be assumed as 9.81 meter per second square. And we can also calculate T2 as T1 minus alpha Z2 minus Z1, because the equation here can always be written as T2 minus T1 upon Z2 minus Z1 equal to minus alpha. And when you simplify it, you get the value as T2 equal to T1 minus alpha into Z2 minus Z1. Now, if this is clear, what we can do, we will go back to this example. Now, if we know T1, we can calculate T2. If we know P1, we can calculate P2. We already know Z1 and Z2 based on the discretions that we have taken, which is 2000, 2000 meter and so on. And once these three quantities are estimated, we will worry about W and E later. So what we will do, first of all, we will calculate the value of density of air at level 1, which is given by PA1 divided by RAT. We know that atmospheric pressure is given as 101.3 kilopascal. I just mentioned that we will use the value of RA as 287, and the temperature is known as 30 degrees Celsius, which would be 303 Kelvin, and this density of air at ground comes out to be 1.16 kg per meter cube. And we will highlight this result. This would be useful, and we will say that this is number one calculation that we have done. Similarly, we can calculate T2. T2 would be T1 minus alpha. Alpha is 6.7 degrees Celsius per kilometer, or 6.5 degrees Celsius per kilometer as given in the question. We can write this as 0.0065 into 2000 minus 0, which implies T2 would be 30 degrees minus 0.0065 into 2000, which comes out to be 17 degrees Celsius approximately. And now that we know that T2, we can calculate rho A2 as PA2 divided by RAT2, which comes and we don't know, we know the T2 RA, but we don't know PA2. So PA2 can be calculated as the function that we just derived, which is P1 into T2 upon T1 divided by G into alpha RA, and substituting the values here. So this is 101.3, T2 we calculated, and all these calculations, whenever we are using inert gas equation, all the calculations are in Kelvin. Whenever we are using the equation of the curve of saturation or the saturation curve, all the calculations would be in degrees Celsius. So this would be 101.3. In denominator, we would have 303 Kelvin. In numerator, we are going to have 290 Kelvin raised to power 5.26 after substituting the values of these constants here. So PA2 comes out to be 80.4 kilopascal. So again, we will go back to figure and we will say that we have determined T1 as 30 degrees Celsius. T2 has been determined as 17 degrees Celsius. P1 was known as 101.3 kPa. P2 has been determined as 80.4 kPa. Our Z1 was 0. Our Z2 was 2000 meter. Now we are left with calculation of E2, E1, W2, W1 so that we can calculate all the quantities that we need. Now what to do with E1 and E2? If you read the question carefully, it mentions that this air is saturated. So when air is saturated, that would mean we can estimate the values of saturated vapor pressure as ES equal to 0.611 exponential 17.27 T divided by 237.3 plus T. The reason I write this formula every time I get an opportunity, because this is a very fundamental relationship that is used quite a times in climatology, hydrology, as well as meteorology. So important for us to get good grasp of it. So at temperature of 30 degrees Celsius, ES comes out to be 4.24 kPa, and at temperature, this is at temperature of 30 degrees Celsius, at temperature of 17 degrees Celsius, ES comes out to be 1.94 kPa. I leave these calculations to you. All you have to do is substitute the values of temperature here to get this. Now again, going back, we have calculated E as well as E1 as well as E2 because air is at saturation, which implies W2 can simply be calculated in this case as 0.622 E by P, where we will use E2 and P2 here, and W1 can be calculated as 0.622 E1 upon P1. Now we know all these values, so we calculate the specific humidity at height 1 and height 2 as 0.026 kg of moist air, of vapors per kg of moist air, and value of W2 as 0.015 kg of vapors per kg of moist air based on the formula that we just wrote, which is 0.622 E upon P. Now we have calculated everything, and now what we will do, we will again go back to the initial formula that we wrote, is that we are interested to calculate MV, which can be calculated as W times rho A times V. For first, we already know the volume for it would be area of base into height, which is given as 1 meter square into 2000 meter. And what we will do, we will use the average value of omega, which we have calculated at level 0 and level 2000. We will use average value of density of air, which we have calculated at level 0 and level 2000, and we will calculate the average mass of vapors contained in first 2000 meters of atmosphere or first 2 kilometers of atmosphere. So after substituting those average values, we get the values of omega as 0.0205, value of density of air as 1.07 into 1 meter square into 2000, and this value comes out to be 43.7 kilogram. So first 2 kilometers of atmosphere at saturation only contains 43.7 kilograms of water, and we will keep on doing these repeated calculation for 2000 to 4000, for 4000 to 6000, and so on, and we calculate that the total sum of mass of vapor that is present is equivalent to 77 kilogram. And when we convert it to the equivalent depth, we can always calculate the depth associated with 77 kilogram of water is 77 divided by density of water in kg per meter cube, and we use area as 1 meter square. So it comes out to be 0.077 m or 77 mm. So that means that in 10 kilometers of atmosphere, we only have 77 mm of precipitable water. And if even this entire water falls on the earth, we are only going to have a minor storm. And this is not even going to equate to the storms that we might have historically seen in our areas or in our region. So the question arises, what results in the heavy downpour or precipitation that we have to manage as civil engineers, from where these heavy flows are originating, what is bringing this moisture flux, and how to measure that moisture flux. So in the next module, we will understand that how these minor storms get translated to major storms, how to quantify that, and that would be the entire area of precipitation in the context of regional hydrology. Thank you.